Welcome to Ganita Samayaha, an interactive learning space. Children, as I proceed with the teaching, whenever I pose in questions, please answer them. This will help you in the learning process. Also, please don't forget to have the writing materials with you whenever you watch these videos. And after you watch, please subscribe, like and share the video. Today we continue with Real Numbers Part 3. Link to part 1 and part 2 is given in the description box below. So let us get started, children. In the last video, I had given in an assignment. I am sure all of you are ready with it, and so let us discuss the same. The first question was, a man has 532 flower pots. Okay, so he wants to arrange them in rows. And in each rows, how many flower pots does he want to have? Yes, he wants to have 21 flower pots. Okay, children, he has got 532 flower pots and he wants to arrange them in rows with 21 flower pots in each row. So what are we asked to find? We are asked to find the number of completed rows and we are asked to find the number of pots that are left over. So this is a very simple problem. We have to simply divide 532 by 21 to get the number of rows. That's all. But we use our Euclid's algorithm and try to solve this problem. Okay. So the solution goes like this. Using Euclid's division algorithm, we can write the A is equal to 21 into Q plus R. 21 because 21 is our divisor. Isn't it? And we know our A is 532. So 532 is equal to 21 into 25 plus 7. So this tells us that the remainder is 7. So number of flower pots that is left over is 7 and we have got 25 rows. Very simple, isn't it, children? I'm sure all of you must have got it right. Okay. So let us discuss the second question. The next problem that was given us, we were asked to find the HCF of two sets of numbers. So the first set of numbers was 340 and 412. So these are the steps that we need to follow and the answer is HCF is equal to 4. Okay, children. And the next set of number was 867 and 255. So these are the steps and we have our HCF is equal to 1. Please verify if you have got all these steps with your answers, children. Okay. So, hitherto we have learnt about Euclid's division algorithm and seen how we can find the HCF of the given set of numbers. So, we will now learn another concept with respect to using this division lemma, children. Let us proceed. So let us look into this problem, children. We need to use Euclid's division lemma. So use Euclid's division lemma for what? To show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Okay. We are required to show that suppose we have a as some positive integer. Okay, we have to show that a squared will be either 3m or 3m plus 1. So, how can we express a in terms in the format of Euclid's lemma, children? We need to know the divisor. So, the clue lies in this 3m or 3m plus 1. That means what? Our divisor must be 3. So, that is the clue. So, we have some integer a and the divisor is 3. Now, how do we use Euclid's lemma to express a in terms of this divisor 3, children? Yes, we can write it as a is equal to 3q plus r. And where r takes values 0, 1 and 2. That is denoted here as 0 less than or equal to or less than 3. That means r takes the value 0 equal to 0 and less than 3. 0, 1, 2. These are the values. Okay. Now what we will do is we have to square this, isn't it? Because we are asked to show that the square of any positive integer. So we have our a is equal to 3q plus r. Let us square this. Squaring a squared means squaring even 3q plus r as well. Isn't it, children? So let us square both the sides, left hand side and right hand side. We have a squared is equal to 3q plus r whole squared. So this is a binomial. We know binomial expansion. We use the formula a plus b whole squared. Okay, so we have a squared is equal to the first term whole squared. 3q whole squared is 9q squared. Then 2 into first term into second term, 6q plus second term whole squared, which is r squared. Okay, children. So this is the expansion of a 3q plus r whole squared. Now, looking into the first two terms, 9q squared plus 6q, we can make out that it is a multiple of 3. Why are we interested? Because our solution must be to show this is of the form 3m or 3m plus 1. That means we must have 3 into something. Isn't it, children? So, we take 3 as the common factor for the first two terms. So, we have a squared is equal to 3 into 3q squared plus 2q. Taking out 3 as the common factor plus r squared. So, this 3 squared plus 2q is some integer m. Isn't it, children? Some integer. So, we will write this as a squared is equal to 3m plus r squared. Okay. So, now the final output or the final result will depend upon this r. Isn't it, children? What are the values of r? We have 0, 1 and 2. So, we will use those values 0, 1 and 2 to establish this relation whether we are getting 3m or 3m plus 1. This is a general formula. Isn't it? We have only generalized that. We have taken a is equal to 3q plus r and generalized that a squared must be equal to 3m plus r squared. In particular, we are bothered about this r square to decide whether it will be 3m or 3m plus 1. Is it clear, children? 3m we are sure. This will be 3 into some integer m. Okay. So, we have got 3m, but this r squared we have to be very specific. Okay. So, we will take all the three cases. We will consider first r is equal to 0. When r is equal to 0, what happens to a squared? A squared is equal to 3 into m plus 0. So, a squared becomes 3m. Is it clear, children? So, when r is 0, we have a squared as 3m. That is, the square of the given positive integer will be 3m. Okay. Or can be 1 as well, isn't it? When r is equal to 1, what happens to our a squared? A squared is equal to 3m plus 1 squared. 1 squared is 1. So, when r is 1, then our a squared, the square of the given integer is of the form 3m plus 1. And when r is equal to 2, our a squared will become equal to 3m plus, we are using this, a squared is equal to 3m plus r squared. Okay, children? So, 3m plus r squared, that is 2 squared is 4. So, when r is equal to 2, we have a squared is equal to 3m plus 4. Are we wondering? It is neither 3m nor 3m plus 4. No, we will not stop at this. A little of rearrangement. That's all. Very simple. I am sure all of you would have understood by now. We want plus 1, isn't it? So, we can write this as 3m plus 3 plus 1. So, now what happens is, this 3m plus 3, we can take out 3 as a common factor. That means 3 into m plus 1. It simply means that this first two term is a multiple of 3. Okay, children? Some multiple of 3. M need not specifically be any integer. It just denotes that it is a multiple, children. Okay. So, we can write this as 3m plus 1 because 3m plus 3 is again a multiple. 3m simply denotes that this is a multiple of 3 together. So, 3m plus 3 is also a multiple of 3 which can be written as 3m. Don't think that we have omitted 3, children. It is just a notation here that has been used. Okay, 3m plus 3 itself means it is 3 into m plus 1, which means that it is a multiple of 3. That means we have got the first term as 3 into sum. Okay, children, that is denoted as m here. We have used m only to denote some integer, not as a particular variable. Okay, children. So 3 into m plus 1 means it is a multiple of 3, which we have denoted as 3m. Okay, and then you are left out with this 1. So even when r is equal to 2, we have established that a squared is equal to 3m plus 1. All the three cases, when r is 0, it is a squared plus is equal to 3m. When r is equal to 1, we have shown that a squared will be 3m plus 1. And when r is equal to 2, we have shown that a squared is equal to 3m plus 1. Is it clear, children? This is how you will work out this problem in case this is asked. Okay, very simple. Let the integer be a, and we know that the divisor is 3. How did we get that? From this statement. This is the clue to tell us divisor is 3. So with that, we can write the general form of Euclid's division lemma. We can write this as a is equal to 3q, a equal to 3q plus 1, and a equal to 3q plus 2, isn't it? Same thing is doing, but in a condensed form. We are writing it in the generally as a is equal to 3q plus r, where the value of r will be 0, 1 and 2. Those values we are arguing it here. That's all, children. So that this step is done so that we get one generalized statement here, and then using this generalized statement, it is easy for us to argue logically. That's all. So we would consider a is equal to 3q plus r, square it and put it into the format of a squared is equal to 3m plus r squared. So we have already got 3m. We have to see what happens to a squared for various values of r. That's all. That is why we have considered r is equal to 0. That means we are substituting r as 0 here. Okay, we got 3m, and here also it was easy. 1 squared became 1. Here there is no confusion, children. We have written it as 3m plus 4, and we have simply considered 3m plus 3 as 3 into some m. Okay, which is an integer. So 3 into m, multiple of 3 we get here. First two terms plus 1. Okay, so this is how we have proved that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Hope this is clear, children. Very simple, isn't it? Please practice this. Don't take it out from memory. Please understand the concept here and then do it. Once you understand concept in mathematics, children, maths is very easy and very interesting. Okay, please don't take anything from memory. You already know. All these are known only. You know what a is. You know when the divisor is 3, how to write it using Euclid's division lemma. After that, it is just simplification and logical analysis. That's it. Okay, let us do one more problem, similar type. So we will use Euclid's division lemma to show that the cube of any positive integer, there we did square, now cube is of the form 9m or 9m plus 1 or 9m plus 8. So looking into this statement, I am sure all of you would have understood what our divisor is. Yes, our divisor is 9, and let a be any integer. So what is the statement that we can write using the Euclid's division lemma with respect to a? A is equal to 9q plus r, and what are the values that r can take? 0 and it can take up 0 and less than 9. Okay, 0 less than or equal to r means r can take up the value 0, and any value less than 9. It cannot take 9 less than 9. That means 0, 1, 2, 3, 4, 5, 6, 7 and 8. Okay, now we are asked to cube here. Okay, show that the cube of any positive integer. So what should we do? Consider a equal to 9q plus r and then cube it. That's all. There we squared, here we have to cube it. So we have a cube is equal to 9q plus r whole cube. Okay, so we know how to expand this a plus b whole cube formula. Very simple. A cube plus 3a squared b plus 3ab squared plus b cube. So let us use that formula and expand this. We have 8 to the power 3 is equal to 9q whole cube, which is nothing but 9 cube into q cube plus 3 into a squared into b. 3 into first term squared, 9q squared. So that will become 9 squared q squared into second term r plus 3 into first term into square of second term. 3 into 9q into r squared plus second term cube r cube. Okay children, we have simply applied a plus b whole cube. There is something very interesting here again. See, the first term is got 9 cube. That means this is a factor of 9. Second term also is a factor of 9. Third term is also a factor of 9. That means the first 3 terms are a factor of 9. So we can write this as 9 into something. We are only left out with this r cube. So that makes our work very easy, isn't it children? So we have a cube is equal to 9 into something plus r cube. So this something we will denote it as m. So we have a cube is equal to 9m plus r cube. So for various values of r, again here 0 to 8, we have to see whether a cube is of the form 9m or 9m plus 1 or 9m plus 8. That is all. So once you finish this, the rest are all just a substitution and then a little of interchanging. That's all children. Very easy. The concept is we know 9a is equal to 9q plus r. We have to cube it. So we are cubing it. On the right hand side, we are using the a plus b whole cube formula and we are expanding it. We are noticing that the first 3 terms has got 9 as a factor. So take that as a common factor. Okay, so all these will simplify down to some integer you will get, isn't it children? When you simplify whatever you have got within the brackets, you will get some integer, we call that as m. So finally we get that a cube is equal to 9m plus r cube. Now we have to argue for various values of r, what happens to a cube we will have to see. Okay, so let us start. First we will consider r is equal to 0. When r is 0, what happens to a cube? A cube is equal to 9m plus 0 cube, which is nothing but 0. So we have a cube is equal to 9m. Very simple. We have got the first one. Next, r is equal to 1. Then what happens to a cube? 9m plus 1 cube, which is nothing but 1. So the next is also clear now. We are happy. Next, r is equal to 2. So a cube will become equal to 9m plus 2 cube, 8. See, we have got the first 3 either in the form of 9m plus 1 or 9m plus 8. We are happy, isn't it children? So next, r is equal to 3. Let us see what happens. When r is equal to 3, a cube will become equal to 9m plus 3 cube, which is 27. But again 27 is a factor of 9, isn't it? 9 into 3. So both the terms is a multiple of 9. That's all. So we write it as a cube is equal to 9m only. Here don't think that we have neglected 27 children. This means that a cube is equal to 9 into some m, some integer m. Is it clear? We have not neglected 27. This is simply a symbol used to write that a cube is of the form 9m. 9m plus 27. This is also 9 into 3. So you will have 9 into m plus 3. That m plus 3 is some integer m. Is it clear children? So we have written r, when r is equal to 3, we have a cube is equal to 9 into m. Clear? Next, when r is equal to 4, let us see what happens. A cube will be equal to 9m plus 4 cube. 4 cube is nothing but 64. 4 into 4 into 4 is 64. So the 64 seems very odd. We want 9m plus 1 or plus 8. Isn't it children? So do a little of jugglery with 64. We know that 64 is 63 plus 1. Why 63 we have chosen? Yeah, 63 is divides 9. That's the highest number within 64. So a cube is equal to 9m plus 63 plus 1. So 9m plus 63 is a multiple of 9, which we will denote it as 9m. Is it clear, children? This 9m plus 63 is again a multiple of 9. So we will write this as 9m and we have got plus 1 there. Okay. So when r is equal to 4, a cube is of the form 9m plus 1. We are only trying to say it is of this form. Okay, don't get confused here. 9m plus 63 plus 1, it's not that we have neglected 63. We have simply considered that 63 is also a multiple of 9. So 9m plus 63 is a multiple of 9, which we have written it as 9m. So, and we are left out with 1, 9m plus 1. Okay, children. Next we have r is equal to 5. When r is 5, let us see what happens to our a cube will become equal to 9m plus 5 cube. 5 cube is 125. Okay. So again this 125 we should express it in terms of the factor of 9 with a remainder. Okay. So that becomes 9m plus 117 plus 8. And this 117, see here children, 117 is 7 plus 1 plus 8. When you add these digits individually, 9. So it is a multiple of 9. Okay. So again, this 9m plus 117 is some multiple of 9, which we write it as 9m and we have got plus 8. So when r is equal to 5, we have got a cube is equal to 9 plus 8. 9m plus 8. Okay. Next, when r is equal to 6, let us see what happens. A cube will become equal to 9m plus 6 cube, which is 216. Okay. Now let us add these digits individually. 6 plus 1, 7 plus 2, 9. So this 216 itself is again a 216 itself is a factor of 9. So it is 9 into something. So 9m plus 216, completely this integer, whatever you get, will be a multiple of 9. Okay. So we can write this as 9m. Clear, children? So when r is equal to 6, a cube is 9m. Then when r is equal to 7, a cube will become equal to 9m plus 7 cube, which is 343. So a cube is equal to 9m plus 343. So when you add this, each digit of 343, we get 3 plus 4, 7 plus 3 is 10. So 1 short, isn't it? It has to be 342 will be divisible by 9. 10 is not divisible by 9. 342, 1 less than that. So very easy to write. 9m plus 342 plus 1. So 9m plus 342 is again some 9m in the sense that it is a multiple of 9. 9m is a multiple of 9. 342 is a multiple of 9. So 9m plus 342 is a multiple of 9, which we are writing it as 9m plus 1. Okay, children. Next, when r is equal to 8, the last one. Okay, a cube will be equal to 9m plus 8 cube, which is 512. 5 plus 2, 6 plus 2 is 8, which is not divisible by 9. Okay, 8 less than 512, 504. 5 plus 4 is also 9. So we have 9m plus 504 plus 8. Okay, children. So this 9m is a multiple of 9. 504 is a multiple of 9. So 9m plus 504 is a multiple of 9, which we are denoting it as 9m plus 8. Okay, children. So we have seen that for all these values of r equal to 0, 1, 2, 3, etc. up to 8, all these numbers are either of the form 9m, 9m plus 1 or 9m plus 8. Do we have anything else other than that, children? And see the order, beautiful. R equal to 0, 9m, then 9m plus 1 and then 9m plus 8 and then it repeats. See, for 3 it is again 9m. For 4 it is 9m plus 1, 5 is 9m plus 8. So beautiful, isn't it, children? Again 6 is 9m, 7 is 9m plus 1 and 8 is 9m plus 8. And there is such a lot of beauty even in mathematics. This, look at the orderness, look at the discipline. So from maths we have a lesson to learn also for ourselves, children. We must be also disciplined like this in our life. Okay, so we have got a lot of values also to learn from mathematics. Okay, children, I hope you all have understood this. There is no confusion at all. Okay, children, please understand the concept behind it and then do it. It will be very smooth sailing. Don't try to mug up, write all these 10 times in your book. No, you should know the concept. As soon as you see this 9m, you should know that your divisor is 9 and you must be able to write this. A is equal to 9q plus r. Okay, we are asked to cube. The question itself is the answer, children. That is the beauty in mathematics. In the question itself, the answer will be there. Okay, we are asked to cube, so we will cube it. And then we want it of the form 9m plus something. Okay, so we will try to rearrange it and bring it to one standard form. Now our work is easy. Go on substituting various values of r. Okay, so then you and after that and some places you will just require this little rework. Okay, a little of integrating it. Okay, that's very easy. When you see 64, you know it as 63 plus 1. When you see 125, you should know it as 117 plus 8. And we have also seen this pattern, beautiful pattern. When it is 0, 9m, when it is 2, 9m plus 8, when it is 3, 9m, when it is 0, 9m, 1, 9m plus 1, 2, it is 9m plus 8. Then for 3, it is repeating. 3, 4, 5, it is repeating. So, knowing this itself, you should know that you should, for r equal to 4, you should get 9m plus 1. For r equal to 5, you must get 9m plus 8. So, accordingly, you can simply try to write it. Okay. Here again, r equal to 6, it is 9m. R equal to 7, 9m plus 1. R equal to 8, 9m plus 8. So knowing this pattern also, you must be able to rearrange it a little properly. For example, r equal to 5, you know you should get plus 8. So you can write this 125 minus 8 is 117. So you can write it as 117 plus 8. And you know that it is a multiple of 9. Similarly, r equal to 6, 216. When you add these digits also, you know you get 9. It's a factor of 9. So it is easy for you to write this as the entire both the terms will be in multiple of 9. So that way you can analyze it. Okay, children, fine. Hope you have understood. Please recollect how this concept has been developed and then do it on your own. Don't try to take it from memory after this step and writing it so many times and seeing. No, once you understood the concept behind, maths is very easily. You didn't have to take much time to work out also. You know all these concepts means if you are thorough with handling such simplifications and all, then it is very easy. Okay, children. So these are the concepts that we have learnt with respect to Euclid's division lemma. Okay, now we will understand something more about real numbers. Under real numbers, we are still understanding about the various concept with respect to integers, isn't it, children? So we have seen how to use Euclid's division lemma on integers. Various. We learned how to find the Hcf and Lcm, and now we learned how to logically analyze whether a given number, when it's squared, what is the format, when it is cubed, what is the format. Is it clear, children? Now we will have to understand more concept. For that, we'll have to take a small recap about some concept that we have already studied in the lower classes. So let's see what it is now. Yeah, we will study something about prime and composite numbers. I'm sure all of you remember those words, those terminologies, prime number and composite numbers. I'm sure you all know what prime numbers and what composite numbers are. Isn't it, children? So what are prime numbers? Yes, numbers that can be expressed as the product of itself and one only. Okay, so if you consider number 2, you can write it as 2 into 1. Itself is 2 and 1. That's all. There will not be any other factors. Such numbers are called prime numbers. And what are composite numbers? They can be expressed as product of primes. And they will have more than 2 factors. Okay, suppose we consider 6. The factors of 6 are 1 into 6, 2 into 3, isn't it? So 1, 2, 3, 6. There are 4 factors. That means more than 2 factors. Prime numbers will have only 2 factors. Composite numbers will have more than 2 factors. Okay, and all prime and composite numbers are positive. They are only positive integers. Then that is also a very important condition for prime numbers and composite numbers. So having known about prime numbers and composite numbers, can we categorize all the numbers that we have into prime and composite, children? Or are there number which cannot be categorized into these two categories? Yes, you got it right. We have got two numbers. What are they? 1 and 0. 1, does it belong to prime or composite? It does not belong to either prime or composite. Why? Because the factor of 1 is 1 into 1, which is nothing but itself only. There is nothing else other than itself. Isn't it, children? So, we don't say that it is a prime number, nor is it a composite number. So we cannot categorize it either under prime or composite because it does not fall into the definition of either prime or composite. Okay, children. And then what about 0? Yes, 0 also we cannot categorize it into either prime or composite because 0 has got infinite factors. 0 is equal to 0 into 1 into 2 into 1000 into lakh into etc. You'll get 0 only, isn't it? And also 0 is neither positive nor negative. That is another condition that we have. All prime numbers and composite numbers must be positive. But 0 is neither positive nor negative. So it does not fall under the category of either a prime number or a composite number. Okay, children. So these are the facts that we already know and we have just looked into it. So basing on this, we will be analyzing a few numbers, whether they are prime or composite. Okay, children. For example, let us take one particular example and try to understand so that we can extend the same logical analysis to other numbers. For example, if we have say 27. Okay, children, 27 can be written as 1 into 27, 3 into 9 or 3 into 3 into 3. So this means that 27 has got factors as 1, 3, 9 and 27. So what can you say? Is it a prime number or composite number? Yes, it is a composite number since it has got more than 2 factors. Okay, hence 27 is a composite number. Suppose we consider the number 29. What happens? 29 can be written as 1 into 29 only. Okay, so that means that there are only 2 factors, 1 and 29. Okay, so it has only 2 factors, hence 29 is a prime number. Okay, children, so this is how we will try to establish a few more results. Say we are asked to find if this given number here, can you see here, children? 7 into 5 into 3 into 2 plus 3. Whether it is a prime number or a composite number. Is this a composite number means what? If it is a composite. If it is not so, then it must be a prime number. So we have to discuss whether this is a prime number or a composite number and we have to justify the answer. Okay. So what do? We take this given number. Okay. This given number 7 into 5 into 3 into 2 plus 3. Okay. When we closely observe here, we can make out that 3 is a common factor here. Is it clear, children? This product of 7, 5, 3 and 2 will be some integer which is a multiple of 3. So this is 3 into some number plus 3. That means what? 3 is the common factor for these two terms. There are two terms here. One term is 7 into 5 into 3 into 2 plus the other term is 3. So we take 3 as a common factor and we can write this as 3 into 7 into 5 into 2 plus 1. Okay. So whatever we have got within the brackets can be now simplified and we can write this as 3 into 71. 7 into 5 is 35 into 2. 7 into 5 is 35 into 2 is 70 plus 1 is 71. So this entire number 7 into 5 into 3 into 2 plus 3, whatever we have given, that given number has been expressed as a product of 3 and 71. That means it has been expressed as the product of two prime numbers. Okay, if we can express them as a product of two primes, then it must be a composite number. This is how we establish. Okay, children, very simple. If such problems are given, just take it and simplify it. You will be given some number, something that will be the common factor for both. Okay, so just take it, simplify it, and then from the result you will be able to express this as the product of two or more primes. If so, then it must be a composite number. Just that is how you justify it. Is it clear? Shall we do one more problem on similar type? Okay, now let us consider another number. The number that is given here is 7 into 11 into 13 plus 13. So this is the format with which you will be given the questions, children. Can you see that 13 is a common factor here? Okay, so we will have a common factor. So you will have to take out that common factor, simplify it, and then factorize it to its prime factor form, and then establish the relation that since they can be factorized and they have more than two factors, they are composite number. This is the general format that we follow. Okay, so the first step is to consider the number that is given to us. Take the common factor. Here it is 13. 13 is a common factor into 7 into 11 plus 1. Okay, so we are just going to simplify it further. This can be written as 7 into 11 is 77 plus 1 is 78. 78 can be factorized further, and now we have got 2 into 39 for 78. 39 again we know that can be factorized. So go on simplifying it till you cannot factorize it further. Okay, so here we have reached a stage when all of them are prime numbers. 13, 2, 3 and 13 are all prime numbers. We cannot factorize this further. So we write this as equal to 13 squared into 2 into 3. So we have expressed the given number as a product of more than two primes. Isn't it, children? So if we can express any given number as a product of more than two primes, then it has to be a composite number. So since 7 into 11 into 13 plus 13, that is whatever we are given, can be expressed as product of more than two primes, it is a composite number. So this is how we have established whether a given number is a prime number or a composite number. I hope this is clear, children. Okay, so now we proceed to understand yet another very important concept, children. Are you all ready? Yes. Let us go ahead. All these are very small concepts and very simple concepts that I've already learned in the previous classes, children. Just a little refining of it. That's all. We know what are prime numbers and composite numbers when you are given any number. This is just a little addition. You'll have to simplify it and then you have to decide. That's all. Nothing else. Okay. It is the same thing in a new form. Just as I keep saying, old wine in a new bottle. That's all. Okay, children? Okay. Now, we will learn one more nice concept, children. Very interesting. Suppose we want to factorize 240. We know that there are various forms of factorizing. That is, we can express 240 in different forms initially. Okay. So, when I consider 240, I could write this as 24 into 10, or we could write it as 8 into 30, or we could write it as 12 into 20, or 15 into 60. So these are the various methods of writing it. Okay, but then we feel that there are different ways of writing the same number 240. Let us see whether we are right in our understanding or not. Okay, children. But now when you look at these numbers 24, 10, 8, 30, etc., we know that they can be factorized further. Okay, so let us factorize each of them further and try to see whether we get the same factors for all the types, or are all of them again different. Okay, so let us proceed. 24 is written as 6 into 4 and 10 is written as 5 into 2. Again 8 can be written as 4 into 2 and 6 can be written as 6 into 5. So also 12 can be written as 6 into 2 and 20 is written as 4 into 5. Similarly, we write 15 as 3 into 5 and 16 as 4 into 4. So now on observing that, we find that we can factorize 6, 4, etc. further. Isn't it, children? So wherever we find such composite numbers, we will factorize them again into product of its prime. Okay. So 6 is written as 2 into 3. 4 is written as 2 into 2. We are left out with 5 into 2. So we proceed like this and we write 4 is again written as 2 into 2 and 6 is written as 2 into 3 here. Okay. And then the rest we keep it as it is wherever we cannot factorize it further. So also we complete it. Okay. And then we notice that something very interesting here. See here, children, in the first case, 2 has been repeated how many times? 1, 2, 3, 4 times. So in the second set, 2 has been repeated 1, 2, 3, 4 times again. Third one, 1, 2, 3, 4. The last one also 1, 2, 3, 4. So, and then what else is left out? 3 into 5. Here also only 3 and 5. Here also 3 and 5. Here also 3 and 5. That means what? Finally, all of them are zeroing down to the same product. 3 into 2 to the power 4 into 5. Or we could write it as 2 to the power 4 into 5 into 3. Or we could write as 5 into 2 to the power 4 into 3. Or 5 into 3 into 2 to the power 4. The way it is written is different, that's all. That means the order is different. But we know A into B into C or B into C into A. They all mean the same thing. Isn't it, children? Finally, we have got the product as 3 into 2 to the power 4 into 5. That's all. All of them have got the same products. The prime numbers are the same. Okay. What does this tell us? This tells us that 240, when we are trying to factorize it, there is one and only one way of expressing it finally as a product of prime. Is this true only with 240? 240 we have taken it as an example. Okay. So any composite number if you take and you try to factorize it to the prime factor form, finally all of us will get one and only one way of writing it. That means there is one and only one way of writing it. That means there is a unique way of writing it. Okay. So if you take any composite number and if you are going to factorize it, there is only one unique method of expressing it, except for the orders. We are not bothered about the orders. We are only bothered about the factors that we get. Okay. So the prime factorization of a natural number is unique except for the order of its factors. So this is a very, very, very important concept that we have understood now, children. And this has got a very special name and it is called as the fundamental theorem of arithmetic. So it is this fundamental logical theorem that has helped us to establish much more concepts that we will study now. So what does the fundamental theorem of arithmetic state? It states that every composite number can be expressed. That means what? It can be factorized as a product of primes and this factorization is unique apart from the order in which the prime factors occur. So there is one and only one solution for any composite number when we are factorizing it into its product of its primes. Is it clear, children? So with this understanding, we will now proceed on to learn something about Hcf and Lcm. Okay, children? Okay. Now let us try to find the prime factors of 140 and 3825. Okay. This is very simple. We have all done it with in the lower classes. But then what we are bearing in mind is whenever we are bringing it to its prime factor form, there must be only one solution. Just to establish that, we are doing this. Okay. So 140 can be written as 14 into 10. It can further be factorized. And so 140 is equal to 2 to the power 2 into 7 into 5. So this is the only way we can express it. Now, according to our fundamental theorem of arithmetic, there cannot be any other factors. No one can say, no, I have got 3 as a factor. No one can say, I have got 11 as a factor or something like that. Okay, because there is one and only one method. All of you must get 2 to the power 2 into 7 into 5. The factors are 2, 7 and 5 only, nothing other than this. Okay, our fundamental theorem gives us the guarantee that these are all the only factors. So that to establish that, we are doing all this prime factorization. Okay, children. So similarly, 3825 can be initially written as 25 into 153. They can be further factorized, and finally you can write it as 5 to the power 2 into 3 to the power 2 into 17. So how many our children do this? Finally the answer must be this. Okay, and because this is the unique answer, you cannot have any other factors other than 5, 3 and 17. Is it clear, children? Okay. Now, using this prime factorization method, we will try to find the Hcf and Lcm. Okay. So, if you are asked to find Hcf using prime factorization method, you must do this method only, children. If you are asked to use our Euclid's lemma, then you must use the other method. Okay. So, don't interchange. Don't think that you can do it anyway. If you are being asked specifically to do it in a particular method, you must do it only in that method. Okay, so let us now try to find the HCF of 12 and 18. So 12 can be expressed as 2 into 2 into 3, which is 2 to the power 2 into 3, and 18 can be written as 2 into 3 into 3, which is nothing but 2 to the power 1 into 3 to the power 2. So what is the HCF, children? We know HCF means common factor, and it is must be the highest common factor. Highest means what? Between 2 to the power 2 and 2 to the power n, which is the highest common one? 2 to the power 1. 2 to the power 2 is not common, because this second term, the 18, does not have 2 to the power. Highest common one. Okay. So the highest common is 2 to the power 1. That means we take the least power. Okay. Whenever we are considering the HCF, we are considering the least power. The least power will be common to both the numbers that are given to us. Okay. And here we have 3 to the power 1 into 3 to the power, and here 3 to the power 2, which is common. 3 to the power 1 is common. It belongs to both 12 and 18. Okay. So the least power will belong to both the numbers. Okay. So HCF is equal to 2 to the power 1 into 3 to the power 1. That means it is a product of the smallest power of each common prime factor. That prime factors for which it is common. 2 is common. So the least power of the common prime factor is 2 to the power 1. The least power between 3 to the power 1 and 3 to the power 2, which is common to both these numbers, is 3 to the power 1. Is it clear, children? For HCF, we take the smallest power of each common prime factor. Only the common ones we take, and then we try to find the least power. Okay. What do we do for LCM? Let us check. Okay. LCM is equal to what? We have to take the highest power here. It is between 2 to the power 2 and 2 to the power, which is highest, 2 squared into 3 squared. Okay. So for HCF, we take the smallest power of each of the common prime factors. But for LCM, we take the highest power of all the factors. Not necessary to be common. Okay. So product of the greatest power of each prime factor in the numbers. So that is how we find the HCF and the LCM. Let us try to find HCF and LCM of a few more set of numbers. Okay. 72 and 108. 72 can be written as 12 into 6. That can be further factorized, and we can write it as 2 to the power 3 and into 3 to the power 2. So also if you consider 108, it can be written as 12 into 9. On further factorization, it can be expressed as 2 to the power 2 into 3 to the power 3. Okay. For HCF, what should we do? We should take the least power of the common factors. So 2 to the power 3 and 2 to the power 2, which is least? 2 to the power 2. Between 3 to the power 2 and 3 to the power, which is least? 3 to the power 2. So HCF is 2 to the power 2 into 3 to the power 2, which is 36. And what about LCM? Highest power of all the factors that you have. Okay. So that gives us 2 to the power 3 which is highest here, and 3 to the power 3 which is highest for 108. Okay, so we get 216. Okay, this is how we find the HCF and the LCM by the prime factorization method. Is it clear, children? Okay, now we will observe some interesting relationship between the HCF, LCM and the two given numbers, children. Shall we look into it? Yeah, we know that 12 can be written as 2 to the power 2 into 3 to the power 1, and 18 can be written as 2 to the power 1 into 3 to the power 2, and we have the HCF as 6 and we have the LCM as 36. Okay, so we are given two numbers A and B, A and B. Whenever there are two numbers, we consider one as A and the other one as B. Okay, and this is the method of writing HCF within brackets. If you write 12 and 80, it is the HCF of 12 and 18. That is the meaning of this. Okay, children, is equal to 6, and this is LCM of 12 and 18 is 36. That is the meaning. Okay, so let us try to find the product of H and L, that is HCF and LCM. HCF is 6 and LCM is 36. So it is 6 into 36, we get it as 216. Let us try to find the product of A and B. This is A and this is B. Let us try to find the product of A and B. It is 12 into 18, which is also 216. Okay, children, let us check with a few more numbers that we have already found out. Which were the one? 72 and 108. 72 can be written as 2 cube into 3 squared. 108 can be written as 2 squared into 3 cube. That we have already seen it. So what is the HCF of 72 and 108? 36. LCM is 216. We have already done. If you want to do it, the lowest power, 2 to the power 2 into 3 to the power 2. 4 into 9, 36. Similarly, LCM is the highest power, 2 to the power 3 into 3 to the power 3. Okay, so we get 216. Now again let us find out the product of H into L, HCF into LCM, which is 36 into 216. So we get 7776. And let us find the product of A and B, that is 72 and 108. Here also we get 7776. If you want to verify it, please do the calculation on your own, verify it and then proceed, children. Don't blindly accept anything. Okay, you verify if 36 into 216 is this, 72 and into 108 is also this. Okay, okay, fine. I have given to you and all these are all correct. Okay, let us assume it is correct. You can all verify it later. Clear? What have we established from here? What do you understand? H into L is also 216. A into B is also 216 for these set of numbers 12 and 18. And for this set of numbers 72 and 108, we have H into L as 7776 and A into B is also 7776. So what do we establish from these two examples, children? Yes, H into L is equal to A into B. Is it clear? So this is another important concept that we have established with respect to HCF and LCM. And how is this useful? Knowing any three parameters out of these four parameters, the fourth one can be easily found out. Okay, is this clear? Fine. Let us see another important observation with respect to HCF and LCM of a set of numbers. Okay. So let us verify the same thing. Let us do a few more problems and try to find HCF, LCF and then verify if LCM into HCF is equal to product of two numbers. So 26 and 91, 26 can be written as 13 into 2, 91 can be written as 13 into 7. So what is the HCF, children? HCF is the common prime factor and highest. So 13 to the power 1 is common and it is the highest for both. Okay, so we have no problem here. So HCF is equal to 13. What about LCM? It must be the highest power of all the factors. 13 to the power is the only factor that you have. That means it is the least and highest. Okay, there is nothing to compare at all because both are equal. So we have LCM as equal to 13. Product of all the other factors also, highest one, into 2 into 7. It is not only the common one. For HCF, we consider the common. For LCM, we have to write all the factors and express it as their product. So we have LCM is equal to 13 into 2 into 7, which is 182. Okay. Now let us consider 510 and 92. Yeah, and we have to verify with the if h into L is equal to A into B. So we find out h into L, that is 13 into 182, we get 2366, and let us find out A into B, that is also 2366. Okay, now 510 can be expressed as 7 into 3 into 5 into 2, and 92 can be expressed as 2 to the power 2 into 23. Okay. Now what is the HCF here, children? HCF is the common least power. Which is common? 73 and 5 and 23. They are all not common. We have got common as something with respect to 2 only. And here we have to take the least power. Got it, children? So HCF is only 2 to the power 1 and not 2 to the power 2. Because 2 to the power 2 is not common to both these numbers. Is it clear? So HCF is equal to 2. And what about LCM? For LCM, we have to write the highest power. So 2 to the power 2. And product of all other, not only common. 17 also we have to write into 3, into 5, into 23. Okay. So it is a product of 2 to the power 2 into 17 into 3 into 5 into 23. So this is what we get, 23,460. We are asked to verify if h into L is equal to A into B. So let us do that. What is h? 2. 2 into 23,460 we get as equal to 46,920. We will find out A into B, 510 into 92. That is also same. So we have verified that h into L is equal to A into B. Okay, children. So now what if we have got three numbers and we find their HCF and LCM? Will this relation like h into L equal to A into B into C, since we have got three numbers, hold good? Let us verify it. So we are asked to find the HCF and LCM of three numbers, 12, 15 and 21. Okay, we will find it, and then we will also verify if h into L is equal to A into B into C also, children. Okay, so we know 12 can be written as 2 to the power 2 into 3, 15 can be written as 3 into 5, and 21 can be written as 3 into 7. So what is our HCF? So that which is common to all the three numbers, it is 3. Okay, HCF is 3. And what about our LCM? It must be this common one, 3 into 2 squared into 5 into 7. Product of all the factors and with the highest power. So LCM is equal to 2 to the power 2 into 3 into 5 into 7, which is 420. Okay. Now let us find out h into L. H into L is 3 into 420, which is 1260. Now since we have got three numbers, that means we have got number A, B and C. Let us find out the product of A into B into C. We get here 3780. Are the two same, children? 1260 and 3780? No. So this tells us that h into L is not equal to A into B into C. That means the product of the HCF and LCM is not equal to the product of three numbers. It will be only equal to the product of two numbers. So the product of three numbers is not equal to the product of their HCF and LCM. So this is what we have established now. Is it clear, children? Okay. Let us proceed now. So how we use this concept h into L equal to A into B? You are given HCF of 306 and 657 equal to 9. That means we know that one number A is 306 and B is 657, and we have got H as 9. We have to find the LCM of the same set of numbers, 306 and 657. Very simple, isn't it, children? We know that H into L is equal to A into B. So substitute. H is 9 into L is equal to 306 into 657. Simplify it and then we get the value of L. Okay, children. So we have understood how to find HCF and LCM by prime factorization method, and we have also established a relation that H into L is equal to A into B only for two set of numbers and not for more than two numbers. Okay, children. So using that, we have also learned how we can find out one parameter when 3 out of 4 are given. So, likewise, even if you are asked to find H also, same thing, you would have been given L or whether A or B. It is just substituting and simplifying. Okay, children. Now, let us do one word problem with respect to this concept. Okay, so we have got Mamata has a music class every 4th day and art class every 5th day. When will she have both the classes? This is what we have to find. So let us write down what are the days when Mamata has got her music class. When does she have her music class? On the 4th day, 8th day, 12th day, 16th day, 20th day, and so on. Isn't it? Every 4 days she has got her music class, and art class every 5th day. So that means she will have it on 5th day, 10th day, 15th day, 20th day, and so on. So which is the day that she has got both? Yes, she has got both on the 20th day. And then it repeats 20, 40, and so on. But initially she will have it on the 20th day. That is what we have to find. That means what have we done? Here we have written all the multiples of 4. Here we have written all the multiples of 5. And we have got a common multiple which is the least. That means what? We have tried to find the LCM of these two numbers. 20 is the LCM of these two numbers. So that is how we have solved this. Okay, children. So she will have both the classes on the 20th day. So such problems you should know that you must be able to find the LCM of the two given numbers. Let us look into one more situation. There is a circular path around a sports field. So this yellow color region is the sports field and this green color region is our circular path. Sonia takes 18 minutes to drive one round of the field while Ravi takes 12 minutes only. So she takes a longer time. Okay. Sonia takes 18 minutes to go round once while Ravi takes only 12 minutes. Okay. Suppose they both start at the same time and same point and same time. They both are standing at this point. Okay. This is the point both are going to start. Same point, and at the same time they start and they go in the same direction also. Not that one goes like this, one goes the other. They go in the same direction. After how many minutes will they meet again? So they are taking different amount of time to go around once, isn't it, children? When will they come back? Both of them come back to the same point and they will start again. That is the question. So let us just see how they will go around. Okay. So Sonia is taking 18 minutes. See? That means what? And by the time she completes one round, Sonia takes 18 minutes to go round once, children. Okay. So by the time she finishes one, what does Ravi do? He has finished one and then done another half a round. So at the end of 80 minutes, Sonia has completed one round while Ravi has completed 1.5 round. Is it clear, children? So when will both of them come back to the same point? Again, in another 18 minutes, what will happen is Ravi will take this half round and complete one more round and he'll be back here. Okay. And what will happen to Sonia? She will take one more round and she will be back here. So after another 18 minutes, the both are will be at the same point. Okay. This logically we have analyzed it. But then what should we do mathematically? Yes, we have to find the LCM of 12 and 18, multiples. We are not trying to divide here. When we are trying to divide, we will find HCF. Here we are finding the common multiples when they will occur again. Okay, children. So we will find the LCM of 12 and 18. That's all. Very simple. You have to just understand what is happening there. That's all. Okay. So on finding the factors, we find that the LCM is 36. So at the end of 36 minutes, they will all be in the same point. That is how we also analyzed it logically as well. Isn't it, children? So they meet again at the starting point after 36 minutes. So we have try to understand how we can find the HCF and LCM by factorization method, how we can use this to solve some word problems with respect to LCM. Clear, children? Okay. Now we will go to one more concept. Okay. Now observe these numbers 20, 40, 70 and 90. All of these are ending with 0, isn't it? And all of these are also even, isn't it, children? How do we mathematically establish this? 20 can be written as 2 squared into 5, 40 can be written as 2 cube into 5, and 70 can be written as 2 into 7 into 5, 90 can be written as 2 into 3 squared into 5. What do we notice here? 2 is a factor for all these numbers. That means if 2 is a factor, that number must be even. Okay, children? And then 5 is necessarily a factor for all these numbers. That is why they are all ending with 0. Okay, children? So if you are asked to establish whether a given number is ending with 0, two things you should try to find out. 2 must be a factor, which tells that it is even. Okay? And 5 must be a factor. Both are necessary condition. Just one of these condition will not do. If 2 is not a factor, then it does not mean that it is even. Then it becomes odd. Isn't it, children? So such numbers, if there is any odd number, can they end with 0? No odd number can end with 0, isn't it? So this is how we try to analyze it. So understand this properly. Suppose you are given any number, and if that number ends in 0, it must be an even number and it must have 5 as its factor. Okay, so any even number that ends in 0 must have 5 as its factor. So this is another concept that we have understood now. Okay, so we use this concept to analyze whether a given number can end with 0 or not. Shall we do that? So let us check whether 4 to the power n ends with the digit 0 for some value of n. We don't know what is the value of n. Whether it can end 4 to the power n, can it have any number that can end with 0 is the question. So what do? We simply take that number and we factorize it. 4 to the n power n can be written as 2 to the power 2 whole to the power n. 4 is written as 2 squared and whole to the raised to the power n. Okay, we know a to the power m whole to the power n is a to the power mn. So this can be written as 2 to the power 2n. So this 2 to the power 2n is some integer m. Isn't it, children? 2n is some integer m. So we write this 4 to the power n is equal to 2 to the power m. So what does this mean? 4 to the power n is written as 2 into 2 into 2 etc. m times 2 into 2 into 2 into 2 etc. It is written m times. So what are the factors of 4 to the power n? Only 2. Okay, there cannot be any other factor. How are you able to say that? Through our fundamental theorem of arithmetic. There cannot be any other factor for this 2 to the power m. 2 to the power m means it is multiplied only by 2. How many times? M times. So, if for our number to end with 0, 5 should be a factor. So, we can very confidently say that 5 is not at all a factor. Why? We have learnt the fundamental theorem of arithmetic. It is guaranteeing us that other than 2, there are no other factors for 4 to the power n. Okay, children. So we can say that 4 to the power n equal to 2 to the power m implies that there is only one factor, that is 2. There is no other factor other than 2. That means 5 is not a factor. Why are we talking about 5? 5 must be a factor for any even number to end with 0. Just now we have seen. Though 2 is a factor, 5 is not a factor. Though this is an even number, it cannot end with 0 because 5 is not a factor. Okay. And why are we saying it so confidently that 5 is not a factor? We have got our fundamental theorem of arithmetic. So as per fundamental theorem of arithmetic, there are no other factors other than 2. Okay, children. So this tells us that this number 4 to the power n does not end with 0. This is how we logically analyze it and we establish it, children. Is it clear? So such numbers are given, just take it and you factorize it and express it in its simplest form, that is in the form of its prime factors. And then we know the condition that for any number to end with 0, it must be a even number and 5 must be a factor. Okay, how do we know it is an even number? If 2 is a factor, it has an even number. And if if 5 is a factor, then it can end with 0. Otherwise, it cannot end with 0. Shall we do one more problem, children? Yes. Let us check if 6 to the power n will end with 0. Okay. Again, we take that, factorize. That's all. Same procedure we follow. 6 to the power n is equal to 2 into 3 to the power n, which can be written as 2 to the power n into 3 to the power n, which means that there are no other factors other than 2 and 3. Why are we saying this confidently that there are no other factors? Our fundamental theorem of arithmetic has taught us that. So, though this is an even number, it does not have 5 as the factor. So, it cannot end with 0. Is it clear, children? Okay. Let us see another one. Okay. Check whether 15 to the power n can end with the digit 0 for any natural number n. Okay. Let us see how this number is, children. 15 to the power n can be written as 5 into 3 whole to the power n. That means the factors are 5 and 3. Okay. We are happy that we have got 5. But what is our other condition? It must be an even number. For it to be an even number, 2 must be a factor. Here, in this case, though 5 is a factor, 2 is not a factor. Okay. Since 2 is not a factor, this is not an even number. So, this cannot end with 0. So, both the conditions are required. It must be an even number and 5 must be a factor. That means 2 and 5 both must be factors for any number to end with 0. Is it clear, children? Okay. Now consider these numbers 15, 95, 105. What is the common thing that you notice among all these numbers? All of them are ending with 5. Okay. That is one thing. So for them to end with 5, what can you tell about the nature of 15, 95 and 105 with respect to even and odd? All of them are odd numbers. So if they are odd numbers, and then they can end with 5. Isn't it, children? So if they have to end with 5, what else are the condition? Let us explore it. So this is written as 3 into 5, 19 into 5 and 21 into 5. That means 5 must be a factor, 2 must not be a factor. If 2 is not a factor, then it becomes odd. Okay, if 2 is a factor, it becomes even and it ends with 0. If 2 is not a factor and 5 is a factor, then it is an odd number, it ends with 5. Is it clear, children? So, the condition for any number to end with 5 is it should be odd and it should have 5 as a factor. Okay, that means it should not have 2 as a factor and it should have 5 as a factor. Is it clear, children? So all these numbers end in 5. 2 is not a factor. They are all odd numbers and 5 is a factor. So the condition for any odd number that ends in 5 must have 5 as a factor. I hope you are not getting confused. Now let us see whether 6 to the power n can end with the digit 5. Okay, 6 to the power n, we know to factorize it and we can write it as 2 to the power n into 3 to the power n. So since 2 is a factor, this is not odd. For the number to end with 5, it must be odd. That is the first condition. Okay, it is not odd. So there itself it gets ruled out. 2 is a factor of 6, that means it is even. So it cannot end with the digit 5. Okay, next. Can the number 15 to the power n end with digit 5? So we'll take 15 and we will write it as 5 into 3 whole to the power n, 5 to the power n into 3 to the power n. Okay, so here 2 is not a factor, so it is odd, and 5 is a factor. Okay, both the condition are satisfied here. 2 is not a factor of 15 to the power n. So that means it is an odd number and we have 5 as the factor. So this will have a 15 to the power n ends with the digit 5. Is it clear, children? Now let us consider 27 to the power n. Will this end with the digit 5? So 27 to the power n can be written as 3 to the power 3n. So 2 is not a factor, so this is odd. But we don't have 5 as a factor. Isn't it, children? That's all. 2 is not a factor, and so 27 to the power n is an odd number. 5 is not a factor, so this cannot end with the digit 5. Very simple. I'll just summarize this for you all. Okay. Suppose you are given any number a, and upon factorizing, we find that factors are 2 and 5. Then what can we say? It is a number that ends with 0. Isn't it, children? And suppose you find that the factor is not 2 and only 5. Okay? The factor is not 2 but only 5. Then what can you say? Yes, it is an odd number, so it will end with 5. Okay, the number ends with 5. Suppose you have got factor is not 2 and not 5. It is neither 2 nor 5. Then what can you say? The number does not end with 5 or 0, both. Okay, it does not end with 5 or 0. Then the other possibility is factor is only 2 and not 5. If the factor is only 2 but 5 is not the factor, so the number does not end with 0. Suppose you want to find whether the number ends with 0 or not. Okay, children, then you consider this part. Suppose you want to analyze whether a given number ends with 0 or not, we consider this. Given a number, okay, factorize it. If the factors are 2 and 5, then it ends with 0. Okay, factor is only 2 and not 5, it does not end with 0. Okay, same thing, it must have both, must be the kind. If the factor is only 5 and not 2 also, it will not end with 0. Clear? So suppose the factor is, suppose we want to find out whether the given number ends with 5 or not, then the condition is if the factor is not 2 and only 5. It should not be 2 and only 5, it ends with 5. Okay, and factor is not 2 and not 5, it does not end with 5. Okay, children, so you remember this table, you will be able to work out those problems. Okay, children, I hope you have understood whatever has been told in this video. If you have any doubts, please put them into the comment box and I will get back to you as soon as possible. Okay, so let us take a quick recap on what we have learned in today's class. We learnt to use Euclid's lemma and to analyze the format of square and cube of a given number. Isn't it, children? I hope you recollect that. We considered A is equal to 3q plus r, where r lies between 0 and 3, and we squared them and we established that they are of the form either 3m or 3m plus 1. Okay, and cube also. We considered A is equal to 9q plus r, where r lies between 0 and 8, that is including from 0 to 8. Okay, and we cubed that and then we analyzed what is the format. We have found out that it will be of the form 9m or 9m plus 1 or 9m plus 8. So this was the first thing we did today. Isn't it, children? And then what did we understand? The fundamental theorem of arithmetic. What does it say? Any composite number can be expressed as the product of its prime, and that will be only in a unique manner. So that is what we have understood. And then we used this fundamental theorem of arithmetic to find the Hcf and Lcm. Application of fundamental theorem of arithmetic in finding Hcf and Lcm. This is what we did. Okay, then later on we went on to analyze whether a given number is odd or even, and then concluded whether it ends with 0 or 5. We also understood about prime numbers and composite numbers and interpreted if a given number is prime or composite. So these are the key points that we have understood today. So as you go through these key points, children, you must be able to recollect what we did. Okay, that is why these key points are given. You can just have this on the screen, and finally you can recollect whether you remember each of this. Did we do this? Did we do this? What does this mean? And then how we found the Hcf and Lcm. There, what else did we do? We established the relation that H into L is equal to A into B, and it is not, H into L is not equal to A into B into C. So all these things you should mentally get it into you, what we learned. And then about this odd and even, whether it ends with 0 or 5, that analysis. We also did talked about prime and composite numbers and how we interpret it. You must be able to get those 7 into 11 into 3 plus 3, something like that, isn't it? That common factor will be there. How we try to express that as product of some prime numbers, and we establish that it is a composite number. So very simple ones that we have done. Of course, we have done a lot, but they're all very small ones. Okay, children. So please watch this video as many times as you want to, and get all your concepts clarified. So as usual, we have an assignment for you. Please look into this and complete it before we meet in the next video. Thank you for watching. Have a good day, and please don't forget to subscribe, like and share this video.